Hi y'all, this is section 3.4, part A, and we're going to learn our second definition of derivative. This is the algebraic definition of derivative. So this will tell you what the equation of the derivative will be for any given x value over the entire domain. Okay? So at first I wanted to review our first definition of derivative. There's only two definitions. The first one is the numeric definition of derivative. That will tell you the value of the derivative at any given c value, but only for that specific c value. Okay? So that was f prime of c, where c was some number, will equal, and don't forget this, the limit as x approaches c. As we're getting closer and closer to that c value, we would say this would be the limit of the difference quotient, f of x minus f of c, all over x minus c, and that's the limit as x approaches c. That will equal the derivative at that specific c value. But again, that guy is only good for that specific c value. We want to be able to make a statement for what the equation of the derivative will be for any given x value or c value. Okay. So instead, we are going to look at just a slightly different setup. So we're going to be talking about the rate of change at our x value. We're still going to move a certain distance away. Okay. The distance away that we move is going to be called h. Okay. So the distance away is called h. And so if you're starting at x and you're moving over h, then that input will become x plus h. Okay. The outputs, if you plug in x into f of x, you're getting f of x. If you're plugging x plus h into f of x, you get f of x plus h. Okay. So h is what we call the tolerance. It's how far away, tolerance, it's how far away from x you are. How far away from x you are. Okay, so you're moving over a certain distance from x, and we call that distance h. And notice that the next definition of derivative will be as h approaches 0. So as that distance is getting closer and closer to 0. Okay, so quick visual. Let's check out the animated graphs. Okay, oh, that's not the one I want. Sorry, I want the other guy. Now I can't move you? What's going on? Oh, sorry, y'all. Okay, here we go. This is the guy I wanted. So, if we look at x, we get f of x right there. Okay? If we look at the tangent line at that point, here's our tangent line. So if we talked about the value of the derivative at x, hopefully we could see that the derivative should be positive because the function was increasing. Okay? This is the whole idea of x plus h. I'm going over some h distance, and then we're going to be looking at essentially the slope between those 2 points. So if I plug in x plus h, the value that I get, and I'm going to be looking at the slope between those two lines, or between those 2 points. And then as h is getting closer and closer to 0, we're going to see what happens to the slope of that line as that point is getting closer and closer to p. So as h approaches 0, that green line should be getting closer and closer to the actual tangent line there. And so that's what we're going to be doing, is figuring out, as h gets closer and closer to 0, exactly what is that slope. Okay, so reset. So if I go back to my thing here, we're going to say that f prime of x, the derivative for any x value, and that's why this is a much better definition. It's the algebraic definition. It will work for every x value. This guy only worked for that specific c value. This will work for every x value. Okay. Still the difference quotient. We're finding the slope between those 2 points. So when we plug in x plus h, what do we get? We get f of x plus h minus the output that we get when we plug in x, f of x, all over x plus h minus x. So there's our difference quotient. There's the slope between those 2 points. And then super important, though, that you remember that you're taking that difference quotient as the limit as h approaches 0. So the limit as h approaches 0. Okay, so you do need to memorize both of those definitions. This is the algebraic definition, and that was the numeric definition. So let's go ahead and just try this out. We're going to use the algebraic definition to find f prime. Okay, so if those are what the instructions say, please write out the definition every time, and then use that definition to find your derivative. So definition is this, that f prime of x will equal the limit as h approaches 0 of f of x plus h minus f of x all over x plus h minus x. Some of you might be thinking right now, well, won't that denominator always equal h? Yes, it will. And you can write that if you'd like. This x minus x will always cancel out. So yes, the denominator will always equal h. But I don't want you to memorize it and think it's like some totally different thing than what we've been working on. It's still just the difference of your two x values. Okay. All right, so if this is the definition, and our function happens to be x squared, okay? So f of x is x squared. I know I'm going to be plugging that in right there, okay? And then this guy says f of x plus h, which basically just means I'm plugging in x plus h everywhere I saw x in my original. So this will still be the limit as h approaches 0. F of x plus h will be x plus h plugged in for x. So x plus h plugged in for x, and it was quantity squared. So x plus h quantity squared. Minus whatever f of x was, which happened to be x squared. All over x plus h minus x, the x's would cancel, you'd just be left with h. So from here, it's mostly algebra. Until the very last step, it'll be a little bit of calculus again. So from here, you're going to have to expand out whatever this is saying. So x plus h quantity squared. We're going to multiply out those binomials. Keep your limit there. Notice I'm moving down my page. Really big. I really want you guys to work down your page as well. Please try not to work across your page. Keep that limit there the whole time. So x plus h quantity squared. X squared plus 2xh plus h squared. Now here, be super careful in other problems to distribute that negative. I know in this example, there's nothing to distribute other than that one term, so just be minus x squared. But in other problems, watch out for that. Okay? And then do not lose that denominator. It's still all over h. Okay? So this might be a good point to start thinking about, all right, I have a limit problem. Anytime you have a limit problem, one of the first things you should try to do is plug in that number. So if I tried to plug in h equaling 0, okay, hopefully you can see that x squared and that negative x squared would cancel, and this has an h and this has an h, so I'd get a 0 up top over 0. So here I have 0 over 0, in a determinant I would have to do something else. Okay, my something else is indeed to collect like terms and to factor. So this x squared and this negative x squared cancel, so I'm left with the limit as h approaches 0, and this should always happen. All of the terms that are left up top should only have h's in it. And so you can factor out an h. If that doesn't happen, you know you've done something wrong. Okay? So h times 2x plus h, all over h. And then this is the magic, right? The h's will cancel. And so now you'll have something that you can actually plug the h into. So the limit as h approaches 0 of 2x plus h. And now this is where you can actually plug in as h gets closer and closer to 0. So you're plugging that in as a 0. So 2x plus 0 would just give us 2x. So remember, all the way at the top, that guy was f prime of x. So f prime of x equals 2x. Now, we will be learning a shortcut, okay? But you are not using the shortcut on these problems. And you need to do this the long way a few times so you can really appreciate those shortcuts, okay? If we could connect this back to section 3.3, when we had graphs. So if I give you a picture of x squared, and I asked you what the derivative would be, okay, graphically, hopefully you know that the derivative right here, that nice minimum, was 0. And my picture's a little off, I apologize. Function was decreasing, so you know you're below the x-axis. Function's increasing, you know you're above the x-axis. So you have a line that looks something along those lines. What I just found out doing the definition of derivative, that the derivative should be exactly 2x. So if I had drawn this perfectly, that derivative right here would be exactly 2x. So it doesn't look like I've drawn him steep enough. It looks like he should be a little bit steeper, but you get the idea. Okay. So that's the definition of derivative using a pretty straightforward equation. And my second example just gets a little bit more challenging because the equation is a little bit more challenging. Okay. So still a parabola, something squared, but to find out f prime of x, we're going to have to do a little bit more algebra. Okay. So the derivative, f prime of x, will equal the limit as h approaches 0 of f of x plus h minus f of x all over x plus h minus x. So the limit as h approaches 0, the bottom should always be h because the x's will always cancel. Okay. Now up top, f of x plus h. You're plugging in x plus h everywhere you see an x in your original. Okay, this one's going to be a lot longer than the last one. So this is 2 times that stuff squared plus 3 times that stuff minus 4. All of that is f of x plus h. So x plus h quantity squared, x plus h. So all of that is the f of x plus h. Now this is where a lot of the errors come. So be careful right here, y'all. We need to minus f of x. So I need to minus all of f of x. I'd highly suggest you put f of x in parentheses so you remember to distribute. Okay, I'm going to have to distribute that negative into all of those terms, which is 2x squared plus 3x minus 4. Okay, so from here you can do a lot of algebra, and this is where I know it gets a little tricky and it gets a little detailed, but stick with it. So x plus h quantity squared, I know that is x squared plus 2xh plus h squared. But then I have that 2 out in front, so I need to multiply all of those terms by 2. So I know at that step I would have 2x squared plus 4xh plus 2h squared. Okay. Now this guy in here, I'm going to distribute that 3, so that's plus 3x plus 3h. Go ahead and bring those down, plus 3x plus 3h. This is all still the limit as h approaches 0. All that stuff over h. Limit as h approaches 0 of all that stuff over h. So I still haven't distributed that negative. I need to write that in. So I'll be minusing 2x squared, minusing 3x, and adding 4. So I guess I could just bring that down here. Minus 2x squared minus 3x plus 4. Okay, so once you've multiplied all the stuff out, at this step, if you go to combine like terms, hopefully you notice that every term that doesn't have an h should cancel out. If that doesn't happen, you've done something wrong, because using the definition of derivative, that should always occur. Okay, so positive 2x squared, there's your negative 2x squared. They're gone. Okay, this has an h, it's not going to cancel. This has an h, it's not going to cancel. This doesn't have an h. So positive 3x, oh good, there's my negative 3x. 3h plus 4. Oh. No, what happened? Oh, look what I did. Okay, I'm not going to stop this video. Obviously, y'all, hopefully some of you noticed it earlier. Look what I missed. 3xh, 3xh. This poor little lonely minus 4, I dropped off. But I knew I made an error because there's no way that that 4 could be sitting there still. It has to cancel out. Okay, and this, maybe I meant to do that mistake because that's going to happen sometimes. These problems do get really long. Try not to lose values. So that was a minus 4 in there. So in here, this should have been a minus 4. And there's the plus 4 and the minus 4 would cancel. Okay. So use that to your advantage if possible. Remember that every term without an h should indeed cancel. Okay. So now I'm left with 4xh plus 2h squared plus 3h all over h. At this point, it'd be a good idea to try to plug in 0. You get 0 plus 0 plus 0, all divided by 0. 0 over 0, indeterminate form. I need to do something else. My something else in this case would be to factor. I'm going to factor out an h. So the limit as h approaches 0 of h times, and let's see what we have left in there, 4x plus 2h plus 3. Now the h's will cancel, and I'm left with the limit as h approaches 0 of 4x plus 2h plus 3. And now I can finally plug in that 0 for the h and see what I get. So we get 4x plus 2 times 0 plus 3, and I am left with 4x plus 3. Okay. Hope that made sense. Sorry about that little mistake there. Try not to make those mistakes, and look forward to discussing this with you in class tomorrow.